Alright, this is the recording for the 4-4 notes for the Big Ideals math textbook for geometry. So today what we are talking about is doing different types of reflections and rotations with figures and seeing if they are congruent. So this first slide here is in your extra practice section of your student journal on page 110. Go ahead and pause the video and see if you can identify which figures are congruent and explain using transformations explaining what moves they made. Okay, so hopefully you attempted it. So I'm going to start with this and point out that quadrilateral ABCD, this one right here, okay, quadrilateral ABCD is congruent to MNOP. Now, if you look at how it changed, it moved to the left 1, 2, 3, 4, 5, and it moved down 2. So we could say that it was a translation of 5 units left and 2 units down, which we know that any translation is a rigid motion, so the shape is congruent, so the pre-image and the image are both congruent to each other. Okay, so now let's find a second set. So we can also look at STUV. So if we look at STUV, it is congruent to this one. It's congruent to EFGH. And if we want to figure out a way to show that it was a reflection, or rotation, or a translation, it is actually a reflection over the line y equals x. Now, I know that by looking just out of practice, but if in doubt, see what you think it might be, and then take a look. You can either just take a look at it by drawing the line in, or you could even use the transformation rules and check some of the points and see if they reflect onto each other. So like V will reflect onto F, U will reflect onto G. And if you check them, they are in fact a reflection over the line y equals x. Okay, so now let's go ahead and pick out a third set. So the third set I'm going to do is triangle JKL. So we have that triangle JKL is congruent to triangle PQR. Now, looking at these, if I just take, for example, point J and point, let's go ahead and go with point P. Point J and point P seem to look like corresponding points. So if I draw in a line to the origin from J and P, not the best line, but we get the picture, it looks like it is a 90-degree rotation. So I could just explain that triangle JKL is a 90-degree rotation counterclockwise of triangle PQR. And we know that rotations also are rigid motions, and so that the pre-image and the image have to be congruent to each other. Alright, looking at number 2. Number 2 wants us to describe a congruence transformation that maps triangle PQR to STU. I went ahead down here and included your various rules. The only one that we don't have on here is y equals negative x. And when that happens, then we not only switch the ordered pairs, but we also change the sign. So you have all of them listed down here, and we're wanting to figure out what is a possibility where it could map. Now, keep in mind that P and S are going to be corresponding points. So somehow P had to move to S, which also means that Q had to move to T and R had to move to U. So just by looking at this, it looks very much like a rotation. It could also be a composition of a rotation and a translation. There are multiple ways to do it. Initially, when I see it, I just think it looks like a rotation. So knowing that P needs to come all the way down here to S, it looks like 180 degrees. So I'm just going to sit here and I'm going to try a 180-degree rotation and see where that ends up at. So looking at P, which is at the point 4, 0, if I just rotate that using the rules, okay, after the rotation, P prime is going to be at the point, and keep in mind this is at 180 degrees, so we keep the numbers in the same places but change their signs. So it's going to be at the point negative 4, 0. So look at where that is, and this is where P prime would be. Let's go ahead and try another point just to get a better picture of what's happening. So Q is at the point 2, negative 3. If I try a rotation, And part of this, guys, you just get better with practice of knowing like what it looks like, but you also sometimes just have to try something and see where it gets you. So if I try Q, I end up with -2, 3. And then why don't I go ahead and try R since we're learning. R is at the point 5, -4. And so when we rotate it, R prime is now at the point -5, -4. I'm sorry, -5, +4. Okay, and so then I'm going to go -5, +4, and I have right here. So this is what my triangle looks like right now. So now it's at least pointing in the correct direction, but it's not quite in the right place. So I feel like how I want to move it. Remember that I'm trying to get P prime to move to S. So I'm going to translate it down 1, 2, 3, 4, 5. So it's a 180-degree rotation, and it is translated 5 units down. And I'm just going to go ahead and write the rule, and I'm just going to put that X stays the same and Y is -5. So this movement is a composition of a 180-degree rotation and a translation of 5 units down. Alright, you could have had a completely different viewpoint of this. It's completely possible that you had a different answer that is still correct. Just make sure you are checking your points. And on the homework, I will try to give as many options as possible when we are grading it so that you know that you got it correct. Alright, number 3. Go ahead and pause the video, see if you can figure out what you think it might be, even if it's just a preliminary guess, and then we'll take a look at it. Alright, so when I see this, first of all, I kind of think of a reflection because I know if it reflected this way, then at least it would be pointing in the right direction. So if I reflected over this line right here, and it wouldn't really matter which line you reflected in, you could always translate it to the right spot later. So if I reflected over this line, and keep in mind that it's a vertical line, so it's x equals, and it's going through 2, so it's x equals 2. So if I reflect it there, C prime is here, B is 3 units on this side, D is 1 unit away, and A right now is 3 units away, so it's 3 units over here. So this is starting to look really good. It just looks like the figure's too high. So then I want to move it down. So I'm going to look at how far I need to move it down. So I'm going to take A prime and try to move it down to E. So it would go down 1, 2, 3, 4, 5. Once again, this one happens to also translate 5 units down. So we would just put translate down 5 units, or we could show the rule and we could do x, y becomes x, y minus 5. And once again, this is just a sample answer. Your answer could have been different and still be completely correct. Okay, on page 111 on number 4 and 5, go ahead and just draw in the 2 figures. Pause the video, draw them in, and then I'll show you the explanation. Also, if you notice K is a repeat of N, they had a typo. I went back and looked, and on a corrected version, they made K the point -2, -1. So go ahead and change that in your student journal and graph that point accordingly. Alright, so hopefully you paused this and drew them in so that now we can look at the math. On this one, on number 4, wants to know, is it congruent, and use transformations to explain. So it clearly looks congruent. It absolutely looks like all 3 sides are congruent to the other 3 sides. So I'm not too worried about that. I just need to figure out how to explain. So this, when I look at it, looks like a reflection over the x-axis. And if you think about it, it's going to change this point negative. This is 2 away, so this is 2 below. This is 1 above, so this is 1 below. So I would say, yes, they are congruent. And my reasoning would be it's a reflection. And you could say in the x-axis or over the x-axis. Either way is fine. And of course, we know that all reflections are rigid motions, so the pre-image and the image are congruent to each other. Okay, on this one, just looking at this doesn't look quite right. So if you take a look here, if you count this line, it is 3 units long. This line right here is 4 units long. So right now, you know that this is not congruent. And you could explain that since we need to use using transformations. We could say that, let's see here, points J, I, and I would say just J and I. So J and I are translated. And let's just see how they are translated. They're translated 1, 2, 3, 4 units to the left, and 1, 2, 3 down. So I would say like this, J and I are translated 4 units to the left and 3 down. But if you look at G and H are translated 1, 2, 3, 4, 5 units to the left, and then 1, 2, 3, 4 down. Okay, I'm sorry, this should have been a 4. So this would show that it has gone 5 units to the left and 4 down. So their vertical translation is the same, but their horizontal is not. So since they were not both translated with the same rule, the same number of units left and the same number of units down, since that didn't happen, they are not congruent. And so they have to be translated by the exact same amount on both x and y to be congruent figures. Alright, so here's a new theorem for today. This theorem is about reflecting things over parallel lines. So what this shows is this shows the line AB, the line segment AB, and it's first reflected over K. So it reflects over the line K. Then the line is then reflected again over M, and K and M are parallel lines, and we know this by the markings right here with the colored in triangle. Those show that those two lines are parallel. So what this theorem says is that when you do 2 reflections over parallel lines, the end result is the same as just a basic translation. So instead of doing 2 reflections, we could have gone straight from the blue line segment, AB, to A double prime, B double prime, with just a simple translation to the right. So what this is explaining here is that the distance between the line is D. The total distance from A all the way to A double prime is the same as 2D. And if you look at Y, this distance right here, this is X, and let's go ahead and let's call this distance right here Y. So really D is made up of X plus Y. The distances that they reflected over the parallel lines are the same, just like how when we're translating over a line on a unit circle, or I'm sorry, on a coordinate grid, we go ahead and we count the number of units away from a line it is. So like if it's 2 above, we go 2 below. Well, it's the same here. If this was 1 centimeter away, we'd go 1 centimeter on this side. Versus if it was, let's say, 2 centimeters away from this line, we'd go 2 centimeters on the opposite side. So these two distances are the same. So you think about this entire distance, it's x plus x and y plus y, which ends up being 2x plus 2y, or the same as 2x plus y. And so that's the same as 2d. So this distance between the lines is d for distance, and the distance from A to A double prime is 2d because it's double that distance. Alright, the other thing we want to point out is that if you drew a line from one point to its image and then to its image after the composition, then you would find out that this line is perpendicular. So this is a perpendicular line to the parallel lines. Alright, so look at your student journal on page 111 and let's take a look at this. So it says a translation maps UV onto which segment. So UV is reflected and then reflected again. But you could just do a straight translation by going from UV to U double prime, V double prime. So our answer is going to be UV maps onto line segment U double prime, V double prime. Now it wants to know which lines are perpendicular to line U double prime. So the line that goes through these 2 points is right there. The lines that are perpendicular to it are line K, it's at a right angle, and line M. So we're going to say line K and line M. Now it says, why is V double prime the image of V? And so it wants us to explain our reasoning. So on this, just taking a look at this, we are going to basically say that the reason it works out is because line K and line M are parallel. So since they are parallel, we know that by doing this, we haven't done anything but we've translated it. So although it could be the image after a composition, it could also just be the image after a basic translation because they are parallel. If they're not parallel, it's not quite the same thing. So on number 9, it says that the distance between K and M, so this distance right here, is 5 inches. And now let's know, what is the length of V to V double prime? But we learned that the length from the first point to the third point, so after we've done 2 reflections, the length is 2 times the distance between the lines. So if the distance between the lines is 5 inches, then the overall distance from V to V prime, or to V double prime, is 2 times 5 inches, so it is 10 inches. Alright, the last theorem today is going to be reflections and intersecting lines. So what we have here is we have line M and line K, and they are intersecting each other. Now, when 2 lines intersect, no matter what 2 lines they are, they're going to make some angle. They're going to form an angle right there. So what this says is that if we reflect a line segment over one of the intersecting lines, and then over the other one, what it actually is a rotation. So we are basically rotating AB to A double prime, B double prime by doing 2 reflections. Now, the angle between the lines, this angle right here, they call X. It's the angle between the 2 intersecting lines that they are being reflected over. The overall angle of rotation is 2x. So let's say this was 30 degrees, it would be a 60-degree angle of rotation. If it was, let's say, a 20 degree, it would be 2 times 20, it would be a 40-degree angle of rotation. Alright, so looking at number 10, it says, what is the angle of rotation that maps A onto A double prime? So if we know this angle, then we can figure out the overall angle. This angle is the same as this angle because of vertical angle theorem. So this is 60 degrees, so this entire thing, 2 times 60 degrees, is 120 degrees. So the angle of rotation is 120. Please write down your questions if you think of any. I'd be happy to clear anything up in class. And thank you for watching this video.